Hello everyone. Welcome to today's quantum spacetime seminar. We are very happy to have Sayantani Bhattacharyya, who would be talking to us about entropy current and higher derivatives theory of gravity. So over to you, Sayantani.
First of all, it's going to be a blackboard kind of talk. Like I'll be writing on this notepad. So something is vaguely written, I'll write over it. And okay, thank you for the invitation and everything. And the second thing is the talk will be, I'll make it a technical kind of talk. So it will be I'm assuming that the audience is a subset of the audience who are present in ISM. So therefore, in Nilay Kundu's talk, he has already told the motivation and all. So that part I'll not do, and I'll directly get into the details of the proof, and I would like to complete it once. I hope that is okay. That's what I prepared for. So let me start the talk. So the title of my talk is entropy current in visible right now, whatever I'm writing. Okay. It's entropy current in higher derivative theories of gravity. Theories gravity. So this is the title, but actually, the way I have understood, it's basically a very specific result of a particular component of Einstein equations, which we have been able to show, if we are correct, I think we have been able to show that it could be recursed in a very particular form. So that basically in a form where it is divergence of some current, a derivative of a divergence of some current. So it could be rewritten in this form, and therefore that form could be used to interpret like a proof entropy current having second law in black hole thermodynamics. So that particular form of rewriting EVV could be used in many different ways. We have used it in some way. It could be used in some other ways, which probably we have not thought about. So what I'll do, though it is about entropy current, I'll not get too much into the details of entropy current and why it is entropy current and so on. But what I'll actually concentrate on is the basic key result, which is this rewriting of a particular component of Einstein equation in higher derivative theory, like the equation of motion in higher derivative theories of gravity, and how it could be written, like how we could show that it could always be written in that particular way. So that will be the basic content of this talk. And then if time permits, then I can get into this discussion of how it could be related to a divergence and entropy current, and how it actually gives to a linearized second law at linearized order and some such things, but which I may not get into that. But the proof of this particular rewriting of Einstein equation would be the key thing in my talk. So what I'll start with is the final result. So the final result is this. So consider a classical theory of pure gravity. And its action has the following. So this is the key result, which then has been used. So I'll just rewrite the conditions. So the action is it visible what I am writing and readable?
Yes.
Very nice.
Invariant under coordinate transformation. Then second thing is Lagrangian density is local, like written in terms of Riemann tensor and its derivatives. In that sense, it's local. And can have arbitrary number of, right? Can have any but finite number of derivatives. So here, because the way the proof has gone, it can have any number of derivatives, but finite, so it's truncated. It's a given action. So in that sense, here there is no field redefinition as of now. Like we have not thought about it also. And you cannot do field redefinition because it's as if it's a truncated Lagrangian. This is the Lagrangian. It's not like it's an approximate Lagrangian. We are doing up to alpha to the particular order and can change it to higher order, something like that. Equations of motion admits black hole type solution. And the key part of the black hole type solution that we are using here is with an event horizon, which is null hypersurface. And the third thing is the event horizon is dynamical. But the amplitude of the dynamics, oh God. Okay, let me just write it. Amplitude of the dynamics is small. And we'll have a perturbation in the amplitude.
When you set the amplitude to 0, is it a killing horizon?
When amplitude is 0, then it's a killing horizon, yes. We'll set up a perturbation. We'll use that fact. That amplitude is 0 is the killing horizon. Then EOM, I'll write this thing and then charge the pencil a bit. EOM, linearized around the stationary black hole. And both indices, equation of motion will have two indices. Both indices projected along xi mu, which is the null generator of the event horizon. Could always be expressed as just a pencil as this. Del V. This is the result. Okay. This is linearization parameter. Like this delta means linearization of this particular. K mu is equal to del V. The K mu del mu is equal to del V equal to the null generator. Oh, this is one thing I have missed. This is on the horizon. And Hij is the induced metric on the spatial slices of the horizon.
Sorry, Sayantani, you had del nu in your on the right hand side of this top equation.
Oh no. They both are del V.
V. And
V is the thing. Sorry. This is no. Sorry. This is del V. This is del V, and this is also del V. V is a particular coordinate.
Yeah, I understand.
Okay, sorry. Along the spatial slices of the horizon. Del I is covariant derivative with Hij.
and the I directions are any direction. V direction is special, but I is not special. Right? I could
I
change
is not special. I could change a little bit. Yes, yes. Along V.
by mixing with V as well.
Can at the moment that's it. But we have suppose we have given choice. Okay, let me now. We have a given choice, and after that we have this structure.
Yeah.
Then naturally this question arises that how things are mixing. That part we have not yet answered yet.
Shantani, okay. What do you mean by spatial slices of the horizon? I mean, horizon is a null surface, right?
Horizon is a null surface, and del V's are these generators of the horizon. These are the null directions, and constant V slices are spatial slices.
On the horizon, constant V slices.
Constant V slices, yeah. So the co-dimension, like one dimension less than the dimension of the horizon, that is this IG indices that are.
Okay, thank you.
Shantani, suppose there was you had a null killing horizon in one choice of the metric variable. Field redefinition of metrics. Does it remain killing horizon?
If it is killing, I think it will remain killing.
It will remain
by making.
Yeah, and it means null surface remains a null surface.
It remains. Then probably null surfaces will remain null surface. By field, you will do field redefinition by Riemann tensors and so on, like out of metric.
Yes.
Then killing will remain killing. This seems to be a null surfaces also probably will remain null surfaces. I have to think about it, but seems like that.
It's true if it was not killing. Right? In general, I think that if you change G mu nu to G mu nu plus R mu nu, what was a null surface in G would not be a null surface in G plus R. In reality. But maybe it's true when it's killing.
Because what I'm thinking that if you have a killing, it's basically this case is going a little faster. There's this boost analysis. So when you are contracting any tensor with this 2 del V directions, it will be a covariant tensor with 2 V indices, if you remember the thing. So what I'll show that in a stationary situations, whenever you have any covariant tensors and indices are contracted with K mu, which is the stationary generator, this killing generator, it will remain 0.
Thank you.
This is far away in the talk, it will come, but you have to remember this thing. It will be a VV component of some covariant tensor, and therefore it will still remain 0. The stationary field.
So you're saying that if I have, a surface that I identify as the horizon,
stationary.
In a stationary situation, that surface is a horizon, is a stationary horizon even after I do field redefinition. It's very
seems like that. I have to think about it in detail. I think it's somehow related to the invariance of world entropy and so on also, their formula. Okay, to think about it. If you do it just by metric, like tensors constructed out of metric.
But I mean, if it's killing in every way, let's say there was a B mu nu field and was even that was killing, I think your argument will probably go through.
Even anything, if all other fields are killing, probably will go through. Yes. And so this is the result, and there will be terms which are nonlinear plus terms that are nonlinear in dynamics. And this JV and JI will be the functions of JV and JI are functions of metric components and their derivatives. So everything is a theory of pure gravity. So only metric is at the moment, only metric is the one variable here. And the second point is JV, once evaluated, So this is just a rewriting of a particular component of EMU. As of now, it has nothing to do with, if I presented this way, it has nothing to do with any entropy or anything. It's just a rewriting. And what I'll show that it could be rewritten always this way, but there is further thing that comes is that JV once evaluated on stationary solutions, it reduces wall entropy. And JI always vanishes on stationary solution. So this is the result. So this is the main calculation that would show. And then this result could be used. So this result could be used to prove the second law, some ultra local form, like with a like no integration over space, no, it is not total entropy. So ultra local form at linear order, at least at linear order in dynamics amplitude. This is how it could be done. This result could be processed to that. That was the topic of Nilay's talk in ISM. He's done it in detail if you have attended it. And there is something called physical process version of first law, for which this could be used. We could not find this in literature. We could not find a general proof of this way of proving first law in a general higher derivative theory. There are specific examples, but what we have done, it could be extended to for a general proof for this thing. And there are some now, there could be other applications in this null symmetries. This one, applications for symmetries in null surfaces, concept current corresponding to that. But we have not done it. But I'll not get into any of those applications. It could be this is the result, which is like a calculational result. It could be interpreted and used in many different ways. I'll not get into any of this.
But
so any question?
Yes, about the application, about the entropy application. You have a result that looks a little bit like del dot j is equal to 0. How does it become del dot j is greater than equal to 0?
Oh, that, okay. It's like, okay, that I can just quickly say. It's basically, okay, this part, this will take a bit of time. Then, okay. The actual equation will be like E mu nu, which is the gravity part of the equation of motion, equal to T mu nu. Okay, there will be some stress tensor or something. This is the actual equation of motion.
Sorry, E mu nu was the full equation of motion?
E mu nu was just the gravity part.
Yeah,
if you're interested only in gravity part, then I can do that.
Yeah, suppose we have no T mu nu to start with.
Suppose I have no T mu nu. Okay.
Only gravitons coming in and out.
Okay. Let's do that here. Only gravitons. Then it is like this. I'll do it. I will do it as quick. K mu. We have K mu, E mu nu, a delta of that. It's looking like del V of, let's write it del dot J, as if like del mu J mu, though it's not exactly del mu J mu. It's something like that, plus nonlinear terms. Now, since there is no stress tensor, this side is just 0. And this nonlinear terms turns out to be, so this is equal to del V of del dot J. Thus this nonlinear 0 equal to del V of del dot C, and nonlinear terms are, let's say, some positive term, manifestly positive, like a squared term, positive term, plus sum of terms which are higher order in alpha. This is the higher derivative. Higher derivative weighting factor, let's say. So this is the length scale which multiplies higher derivative terms. So there will be some terms because of the higher derivative corrections of the equation of motion. This is the positive term which comes from this Raychaudhuri equations, shear square and theta square. And this is from Einstein part of the equation, and this is cleanly positive. Okay, and this is the del dot J. So doing this, what we get is that del V of del dot J, if we assume all the higher derivative terms are very small compared to the contribution coming from Einstein equation, this basically says del V of del dot J is negative. So del dot J is something, it's a scalar function which is continuously decreasing in V direction. So this is del dot J. But we know at V equal to infinity, the black hole will settle down and del dot J, all the terms should certainly go to 0. So something that is monotonically decreasing and at V equal to infinity is going to 0, for every finite V should better be positive. So therefore this kind of a thing says that del dot J is positive for every finite V. Is this clear?
And it's not possible that we would have situations where the Einstein terms are 0, but the higher derivative terms are negative.
It's possible. In that case, you have to figure out how to make it a full square. So if the Einstein terms are 0, that's what we tried for Gauss-Bonnet term before this paper has come out, before this thing, long before 2016. So Einstein term, if there's special cases where Einstein terms are 0 and these higher derivative factors will come, and I'll try to make them full square so that everything is just the usual entropy current story where I'll try to make everything full square. But the only issue there is, compared to the fluid entropy current, just making it full square and making it positive definite, is that in the higher derivative terms, more and more new linear structures are coming. That was not easily handleable because now it's getting a bit, is that what you want to know, that why is for higher derivative term, where the problem could come?
Yeah, I just wanted to know how, to what extent it's a proof. I mean, is it unreasonable that there is a situation where the first term is 0, this Einstein term is 0, and the other terms contribute so that the law will be violated?
So sorry, can I just come in here? No, you should answer, Shiraz, but I don't know the topic as well, but I wanted to just ask the following thing. Why are the higher derivative terms always of a particular sign? Maybe Shiraz is asking something.
Higher derivative terms are not of particular sign. They could have any sign.
Then how do you get the fact that del nu del dot J was less than 0? Sorry, I had to step out.
Assuming higher derivative terms are always suppressed because of this alpha to the n. Like then you are applying perturbation. The higher derivative corrections are all coming in perturbation. Like the more the number of derivative, the smaller they are. Like this alpha is, this higher derivative coupling is a very small number. So Einstein term will dominate.
I see.
So if that is, so that's also a big thing.
It's a derivative kind of proof, is it? I mean, it's a perturbative proof, is it?
Then it's a perturbative proof. The first line that's writing as del V is del dot J, there is no perturbation in higher derivative expansion. But then if you want to convert it to proof of this positive definiteness of higher derivative current, then it becomes a perturbative proof, and then there are meshy issues can come. Like if the Einstein part is itself 0, then higher derivative term, like Einstein part gives a very specific kind of term. It's the shear square, the null generator shear square. If that shear square term is somehow 0, if for a particular kind of profile, then higher derivative term having opposite sign will get that whole proof in a trouble.
Yeah.
So that's what I think Shiraj was asking. Then that could be So then there is a technique of making it a full square.
But you can always you understand that you can always do that.
No. I think I don't understand.
So fine. So the proof is up to the at least in solutions where the Einstein term does not vanish. Is this right?
Proof is up at least in solutions where the Einstein terms does not vanish. If you want to use perturbation, further perturbation applied.
Okay,
then it's a proof.
But
and one more bad thing about this way of proving, because you are asking, is that you are proving that some function is negative definite. Like del V of this thing is less than 0 and therefore del dot J is positive. So if you cannot show that del V of del dot J is not less than 0, not having a particular sign, that doesn't say anything. So this is really the most disturbing part of proving the thing in this way, I feel.
But sorry, I'm sorry, let me take a step. I'm not sure I'm understanding the basic picture. Are we working with Einstein gravity plus small corrections? So the black hole, basically, forget charges, is a Schwarzschild black hole. We all know and love with small corrections due to higher derivatives. Is that the setup, or are the higher derivatives in principle as important as the Einstein term? Sorry, I feel I'm not...
So what I want to say, if you just want to know this much, this is a rewriting of this particular equation. There you don't need to have higher derivative terms to be suppressed or anything.
Okay.
But this is an identity. If you want to further convert it to a proof for entropy positivity, then higher derivative terms has to be suppressed.
That line which you boxed is del nu del dot J plus non-linear terms, right?
Del V.
Del V plus non-linear terms. So you're saying if that was that's what you had to prove, then it can be a strongly curved.
It could be strongly curved or anything.
But from there to state that the nonlinear terms have a particular sign, you have to try and break them up like this.
Break them up, and since the Einstein part has a particular sign and rest are suppressed, therefore everything.
Okay, I understand. But and then just to understand again, sorry, I mean, what would at least be the attempted proof that if the positive terms happen to vanish in all such circumstances, perhaps the higher derivative terms will organize into perfect squares? Is it
that is like this, full square? No, it's like the Einstein term has sigma square. If the higher sigma is something, let's say, no need to specify this. If higher derivative term, the new terms are sigma times something, some another structure.
Okay.
Let's say chi. You make it a full square and have a chi square, then add some extra chi square, and then again make it a full square. And it's an iterative procedure. So we try to do it for Gauss-Bonnet. Even before having this current, we try to do it for Gauss-Bonnet, but we did this thing. This philosophy comes from this fluid entropy current, where we could do it at any order. Like at every order, you can show that you can always make it a full square, like higher derivative term adjusted to it. But here it's always not coming with this kind of a structure effectively. New structures are coming, so there is no proof that it could always be done. Even if we couldn't even do it for Gauss-Bonnet, but even if we could do it for Gauss-Bonnet, we don't have at least till now, I don't have any general structure that this could always be done.
Okay, thank you. Sorry, thank you, please.
Can I ask one question?
Yes.
Hello, Sayantani, by the way. It's Roberto here. So you're saying that the sigma square term, what we usually would say it's the viscous dissipation term that makes the entropy grow. You're saying that it comes only from the Einstein part of the theory? Are you saying that there's no contribution to the viscosity from the higher curvature terms in the axiom?
No, I'm not saying that. Higher curvature can give anything. If it is giving sigma square itself, there is no issue. So the coefficient of sigma square will just change. It won't affect the sign.
Okay, so but the coefficient of sigma square, that depends on the coefficients of the higher curvature terms that you have
the coefficient will change, but if your higher curvature terms are always suppressed, so sigma square, let's say, have one from Einstein gravity, something from higher curvature term, which is of the order of alpha square, cannot even change the sign. So then that will not affect this positivity thing. It will change the coefficient, rate of entropy production, everything, but it will not affect this positive negative business.
but then in that sense, I mean, the proof of positivity is just that in the Einstein theory, you can prove positivity, and then as long as you're not marginal, I mean, as long as you have a
as
finite,
long as things are not just marginal, it's okay. But if sigma is 0, then it will not work.
So the main point is that the linear terms, the terms that were linear in perturbations, can all be put into this J.
All be put into this J, yes. And all the linear terms could be.
Quadratic and higher is just the same as Raychaudhuri, basically.
Quadratic and higher is just the same as Raychaudhuri, yes.
Raychaudhuri plus other things which hopefully don't matter. Yes.
Hopefully don't matter, yes.
Okay, fine. So the core of the proof is the linear terms can be put on one side.
Linear terms could be put in just linear terms, yeah.
I have a question.
Yes.
So usually when you vary the Lagrangian, you get a surface term as well, the del mu J mu term, which usually gives rise to the noise, the current, and so on. When you do the analysis, when you vary with respect to some symmetry. Is the first term del V del dot J related to that sort of term?
It would be nice to see that, but we have not been able to show, like, relate this del dot J with any symmetry so far. Horizon symmetry.
When you vary the action, there is this del mu J mu term present, right? Which is a surface, which becomes a surface term, and you can set
total derivative term.
Yeah, total derivative.
Yeah. It's related to that.
Okay.
This J could be derived from that. We'll use that to derive it. Okay. Okay. Shall I?
Please go ahead.
Okay. But I'll just prove much. It will take a long time, I think. So, and after that, application is not. So now the plan of the talk is this. So first I'll give the setup, which is the coordinates. Like I keep saying del V and so on, coordinates. And then 2, I'll talk about the symmetries. Or basically the residual gauge symmetry of the coordinate. Like once we fix the coordinates, still some symmetries will be remaining. And this concept of stationary will be related to that. Concept of stationarity. And how do you measure the departure from stationarity? You kept saying linear in the dynamics, but you will not explicitly put in any particular dynamics. So particular thing coming in, falling in, or any such way. So how do you departure from stationarity, linearity? And then this thing has been, I should have known this R number, this linearized entropy thing. This has been done by Aronwal before us. So this I'll review. And that will quickly I'll review. So that will give a place like Aronwal has already proved that this particular component of Einstein equation could be written something like this. This much he has already proved. But what we did is adding another Ji to it. This is a part that we have figured out. So I'll place it along with this Aronwal's work. That's why do we need to have Ji? And for entropy positivity, this much is enough, but this is extra what we found. So after doing this, I'll come to the proof. So it will have an identity involving K nu, E mu. Then in this identity, different terms of the identity will be constrained using be constraint using that symmetry I have said, the symmetry constraint using the symmetry. And this identity together will finally give that particular structure. Okay, so this is the way we'll be proving. So I'll just, any question here at this point? Just start with the.
Sayantani, I have a question. This is Amitabh.
Hi, yes.
Yeah. So this relation to Ehrenwall's work. So this, at some point, you will argue that JV and JI form a vector on the null hypersurface.
I don't know what exactly. JI form a vector on the spatial sizes, and JV is a scalar. But they together form a vector on the null hypersurface. I need to study it. I think I don't know exactly what the criterion are. Maybe they do. There is no Lorentz symmetry kind of symmetry.
Yeah, that is true. Yeah.
So therefore, they're not J mu in that sense. But still some transformations are left, and they can mix. And we have not yet explored. We thought of exploring that, how they are mixing. That must have some structure. The mixing of them. Okay. Like, it would have been nice if we can have some symmetry, and using that we could say, instead of going through this proof is convoluted. Instead of going through this, if we can say that because of this symmetry, if JV is there, there has to be MJI. Like the way if there is Lorentz symmetry, in some coordinate JT is there, in some others frame there has to be MJI. Something like that. That would have been very nice. Okay, now choice of coordinates. We have del V, which is this affinity parameter, least affine parameter. Spatial vectors, like the coordinates on the constant V slices, basically. This xi. They constitute a coordinates on the horizon. And then we have del R, which is vectors away from the horizon. They are labeled by V, xi are constants. Like this del R curves, integral curves of this del R are the R coordinate, and which are labeled by V and xi point where they are intersecting this horizon. And R, V. Okay, R is also an affine parameter. R is an affine parameter. I'm saying it this way because this shows that any metric could be cast in this form. And R, V, xi with the coordinates, the full space time.
Is motion along R null?
Motion along R is null, and R is an affine parameter. So it's like you have horizon here. Let's say these are V, these are xi's, and from every point you shoot off this R thing. And okay, you have to also mention what are the angles. Okay, RV xi coordinates of the full space-time. So these are, let's say, V, these are xi, then these are R, but R will shoot up from horizon given angle, full space-time. So which is specified by del R, del I equal to 0 on the horizon. Once you specified it on the horizon, you don't have to specify it anywhere because then R is a fine parameter and null will specify, fix it everywhere. Del R del V equal to 1 on the horizon. To begin with, it is on the horizon, but given that R is null, it's then everywhere same. And if we use all these conditions one by one, the metric turns out to be just this. Okay, and one more thing, sorry. And also we have used the origin of R as R equal to 0 is the horizon. Is the horizon. So the origin of R coordinate along each of these lines, this point where it has intersected the horizon is called R equal to 0. So once we have done that,
what do you mean by del R del V on the horizon?
This is the dot product.
Okay.
It basically says GRV equal to 1, and this is GRI equal to del R comma del I.
Okay.
So it's the shooting angle. So we first fix them on the horizon, but given that R is a finely parameterized null generator, everywhere it is fixed once you have fixed it on the horizon. So it is D square. So this could be systematically imposed on any metric, any black hole type of metric. And if you are starting with car metric or some such complicated black hole metric, this whole going to this coordinate itself is a perturbative, complicated thing, but it could always be done. So that's the main reason I was doing it in this way.
So this thing that you can that it remains true as you move in R, that's like some definition of the xi coordinates away from the horizon, right? That you can choose a definition that makes it true.
That's like a constant V and xi line is these R lines.
Right. Right. And that it remains true for V is less trivial because V was added independent definition because it was killing, right?
So it doesn't. V was killing here. Then here you have a like V was killing on the horizon. No, V was not. Now nothing is killing. Sorry, V is generated on the horizon. Now nothing is killing. It's just the setup.
I see, but you will want to apply the setup to also the case of a killing horizon, right?
You want to, but then you'll want to set up that thing also the case of killing horizon, and that happens automatically then.
Yeah, you're saying that if you do the shooting and defining V, it will be automatic that you will land on the killing definition.
But V is actually, V should be proportional to the killing vector. So V could be, so del V
is not constant.
So that V is not high. You can have something and it will be something else. It's not just del V is not the killing vector.
No, I understand, but I thought you were going to define xi away from the horizon by this condition that lines of constant that as you move along R, as you move along GD6, those are lines of constant x.
So as you move along, those are lines of constant V as well, but V is not a killing vector.
I thought in the beginning of your talk, you said you're going to apply this whole thing to a situation with a killing horizon.
Killing horizon is that you have a killing vector that reduces, that becomes proportional to the generator of the horizon at R equal to 0.
And that generator is del V, right?
So the actual killing vector is, you say, here will be this, R times del R.
Oh, I see.
So if you go to the horizon, it is R equal to 0. There is also a V. So it's proportional to del V on the horizon. It's not affinely parameterized if you.
Okay, fine. Thank you.
Sayantani, can I just use this opportunity to make sure I'm understanding the basic setup properly? If you don't mind, sorry to slow you down. I apologize. So, okay, if I understand what you're discussing is a theory with several higher derivative terms in general, where you have, in principle, can have a very curved black hole to begin with. All kinds of things, that black hole is formed by all kinds of things falling in, etc. Finally, there is a event horizon which forms when you know the full history, and you go along that event horizon and you look at the perturbation to first order of k mu, e mu nu. And that can be written again then to first order in the perturbations as this derivative term on the right.
Yes. Yes.
Is that right? Have I understood properly?
And that event horizon is killing.
Event horizon.
What is that thing, Shiraz? If all kinds of things are falling in, etc., etc., finally the black hole may settle down to something. But what does it mean to say all along that null set of null rays making up the horizon while stuff is falling in and all, it's killing? I didn't understand that. Sorry.
No, it's not yeah, but I think the proof is only for the very late times when it's small perturbations around the killing horizon.
Oh.
It's a small perturbation around the killing horizon.
Oh, okay. Now I didn't understand that. I didn't understand. Okay. Oh, thank you. So this proof is only when you have what's a very small departure from a killing horizon, huh?
It's a small departure from the killing horizon.
Thank you, Shah.
Linearized around the killing horizon.
Okay. Thank you. I was missing that point. Yes, thank you.
Okay.
I have a question.
Yeah.
So when you are saying that you are setting the boundary metrics, you are setting the metrics to 0 and 1 on the horizon, doesn't that mean that the surface term will go to 0?
No, I'm not setting the metric 0 on. It is just the Ri component is set to 0 and Rv component is set to 1. It's like choosing a gauge. You're choosing Rv and Ri component to be something. There is Ij component still there.
Okay.
Yeah, sorry, I have an organizational suggestion if Pushkal will allow me. My suggestion is that we continue this talk at another, so that Sayantani can go at her own speed and then we find another slot to continue it.
Yes, we can do that.
Okay, so just go as slow as you want, Sayantani. We'll find another slot and you continue if you don't mind.
Okay, so the slot I'll be back on 27th.
So we find something
27th December.
for you and where people are back, maybe even in January.
Okay. January is fine. Okay. That would be. It'll take a long. Proof is a bit long.
The proof is long, and I mean it's nice to have these discussions and so on. And
Right.
And now, how long do I have? It's 1 hour.
Since Sandeep has to go at 7 or maybe 7:05 or something like that, maybe you can. I mean, I don't know. Everyone should say, but my suggestion is let's do 15 minutes now and then continue in the next slot.
No. Don't curtail. I can try to watch the video or something. I mean, I hate to. No, please. I mean, whatever you like, but I'll have to run. I'm sorry.
Yeah, I would say, Sayantani, my suggestion would be like something like 20 minutes, stop at a natural spot and we'll continue. Is my suggestion.
20 minutes. Okay. Okay. If we had time, then I could have actually derived the metric also from here, but I'll write it right now. So
we can give you as many slots as you want, Sayantani. Whatever you feel
like.
Okay. But now I'm scared to take on to the derivation because I'm not prepared for it. So I'll just write it and I say which term will come from where. But
wonderful.
This is dxi and hij dxi dx. So if I impose all these conditions, the metric will take this structure. Okay. So here r equal to 0 is the horizon, is the null surface. So x is a function of everything. Omega is also a function of everything. So here r square factor. So when del v is a finely parameterized null generator, it turns out that dv square we can derive it. The dv square will have a double zero on the horizon. Tries null generator. Then the coefficient of dv square will have a double zero on the horizon. That's why there is an r square, because r equal to 0 is the horizon. dv dxi will have a single zero on the horizon. Therefore, there is one r. dr square is 0 because r is a null according to our choice of gauge. And this dv dr is 1, this is this condition, and dr dxi is 0, that is this condition. These are the kind of choices of gauge. But this r square factor and r factor is the fact that dv is an del v is a null direction, and therefore a tangent to the null surface, and therefore this del v del xi has a single zero. And because v is an affine parameter, del v square term has a double zero, and which is this. And then this becomes the metric once all these conditions imposed.
Shanti, I'm going to embarrass myself. If we just look at, I don't know, Schwarzschild black hole in Eddington-Finkelstein coordinates, there we get this dv/dr, and then we get f of r dv squared.
Because their dv is not affinely parameterized.
Ah, I see. I see.
So if you affine parameterize, it will become double zero.
I see.
So all these zero conditions are imposed, and we got this here. So this is the structure of the metric. Once these conditions are all imposed, and they could be imposed step by step on any metric. Schwarzschild we could rewrite in this form with this after affine parameterization. Now I'll come. So this is the metric.
Hello.
Yes.
Just one question.
Yes.
If there is a double zero at the horizon, this parameterization, let's say if I had like a stationary black hole, how do I look at the temperature, Hawking temperature, surface gravity, and so on?
So I think the temperature definition is you have a time like killing vector, which reduces to time at infinity.
Right.
And you have this affinely parameterized. So this time like killing vector eventually goes to becomes proportional to the killing vector on the horizon. And then you can affinely parameterize it. So it will give you a proportionality factor. That factor is the temperature.
So there's no, let's say if x is given as a function of r near the horizon, there's no simple formula, because usually we would have a single zero and then we will look at the derivative. And so
you look at the derivative, it's a temperature, and that derivative that becomes constant when you have a stationary thing on the horizon. And that single zero you have when you have a time, which is actually reduces to the time at infinity. This v is not, need not be time, and even it will be space, like if you have rotating black holes and so on.
Okay.
You see, if you have a flat space rotating black hole, this v direction has del t and omega, this angular momentum direction. And if you then evaluate it in infinity, it will become space-like, because the omega square part, you will have an r square in it.
Maybe let me kind of rephrase my question. Let's say for the Schwarzschild, what will the x be? What will these functions be? Let's say just simple.
If you want to, so what you have to do is to just impose this Schwarzschild derivation. Okay, this is there in our paper in the appendix.
Okay,
1912 paper appendix, not this one, the last one, the one before that. In the appendix, we took Schwarzschild, assumed there is a temperature, and then convert it into this form. Not exactly Schwarzschild, a more general form of that.
Okay. Okay. And,
so it's a bit step by step, but main thing is that there's an horizon generator and another is a time. The relation between this affinely parameterized vector and that time, the killing vector and affinely parameterized vectors of the horizon are proportional to each other, and that proportionality constant is actually giving something like temperature. They're not equal.
Okay, thank you.
Okay. that deviation, that calculation is not difficult because everything is near horizon calculation, but I'm just, I'll do it in the next session if I have, and I can produce it then. So now, okay, now this is the metric, and I'm claiming that all stationary and all black hole kind of thing could be converted to this form, where V is a finely parameterized null generator. And this claim is crucial for the whole analysis. Like, this thing has to be true, otherwise the proof will not go through. Now there are symmetries. See the structure. So we have gauge fixed it in some way that we have fixed dV, dr components. So all R square, RV, and Ri components are fixed by your gauge choice. But still there are some residual gauge symmetries, because the way we did it, we had some affinely parameterized null generator on the horizon, but even after affine parameterization, this is not clean. Like, you can still scale del V by something. Like, if V goes to some function of X times V plus some another function of X, it will still remain affine. So V will remain affine. If we go to this kind of thing. So if and then since the V slicing are changing, so R directions will also appropriately, everything has to change, but it will remain affine and the previous construction could be done. So with a different V, we could still have the same metric, same structure of the metric. It doesn't come, this is like a residual symmetry still left in our gauge choice. So what we'll be doing, and that's what Aronwal has also done, is a much smaller class of this particular symmetry he has used to constrain the structure of the components of the equation. So the structure, the small, this is a complicated one. If I transfer V to Px times V plus Qx, R will change in a very complicated way, because V and X slicing are changing, the angles, the dot products between del R and del V will change in a complicated way. So if you want to keep it in this structure, the coordinate redefinition will be complicated. But one simpler, much simpler version of this is this. Lambda. So if you just look at this, dV dr lambda is a constant. This is a much simpler version of this. P is constant and Q is 0. This is a class of this particular general transformation possible. Now under this, all these components will remain invariant, because R and R square has been multiplied by dV square, R is dV dxi. So everything will remain invariant. So this is something which will be called loose symmetry. Now some terminology that we'll be using. This is the symmetry that we'll be using to constrain the structure of the equation. So under this transformation, any covariant tensor component, this is a coordinate transformation. So we'll transform as, like, it will have the following transformation. Tensor component, a particular component, going to some scale times tensor component, same component, evaluated at an appropriately scale point.
I have a very naive question.
Yeah.
So when you vary the action, you usually end up with the equation of motion plus some 4 divergence term, right? Del mu J.
Yes.
So, but here you are getting a sort of term on the surface of the horizon. Where the 4 divergence term is a bulk term. It encompasses all space.
Yes.
What is the connection?
That 4 divergence term will be used to get this thing, but it's not that 4 divergence term. This J is not that theta. I'll call that theta, the total derivative. It is not that, but it will be used to derive it. It's true that theta is bulk, but here also EVV is on the horizon. And the right-hand side is everything is on the horizon. So I'll use that 4 divergence term to derive this. Even in world entropy, that has been used to derive this, derive world entropy, right? That it's not that 4 divergence term. If you remember the world's derivation, I'll come to it. Okay. Where omega, which I'll name as boost weight, is equal to number of lower V component of that tensor plus number of upper R component minus lower R component. It's a very specific kind of thing. It's a very specific coordinate transformation. So if for any, we know for any covariant tensor component, how it should transform under any coordinate transformation. So if I apply this particular coordinate transformation, if it's very simply, it will follow. It will only affect the V and R index direction. So tensor component, it will have several indices. Only V and R indices will be affected by this kind of coordinate transformation because say V goes to V and R goes to R and just by scaled. And therefore you will get this kind of an weight. So all lower V component plus upper R component will get something +1 and all the upper V and lower R will get -1. Is this clear? That will be like this.
Sayantani, so just to rephrase my earlier question now, so JV will have boost weight -1 and JI will have boost weight 0. Is that correct?
No, sorry. Yeah, what I have written here, according to that, that's what it would have happened. But JV, it's just a name. It's not a V. It's not a tensor V component. So JV is actually boost weight 0. Rather, EVV, the EV component of equation of motion, this is boost weight 2.
Yeah.
So therefore, del V square JV, this is, I should not call JV, let me call it something else. This V has nothing to do, it's not a tensor, it's not a covariant tensor V component of that. I don't know how to covariantize it. The same is true for JR. So it's just a name, it should be written something. It's a 0 weight. This thing is a 0 weight and this thing is a weight 1. Okay. It's just, this is a bad nomenclature, I agree, but that's what I have written.
But the conservation of entropy current, you would like to think of it as del mu J mu. So this interpretation is not there.
This interpretation del mu J mu, you could think of it like that. If it is there should be something like this, but I don't know how to write it in a null surface. How things are mixing. Del mu J mu if there is low range invariance. But on a null surface, there must be some structure, I don't know. In a general surface, it is del mu J mu.
Yeah.
But I don't even know on a null surface what are these full Christoffel symbols. Like square root G is not defined, so I'm not sure.
But we could write it as D of a form, right?
That way I have written. That way I have written it in some complicated way. I don't know whether that will say. We are trying to do it on the transfer it to the fluid side, the way we tried for just Einstein gravity. The same thing we tried to do for the thing. That has some issues, is not complete, and then some form way we could write it.
Yeah, so if the horizon is d minus 1 dimensional, this will be some d minus 2 dimensional form, and then we...
some stuff. Yeah. That way there are some. I'm not sure whether that's a entirely satisfactory thing what we did, but something could be done. This way of writing is very difficult. Okay, that I will do. Okay, so this is the boost weight. It's a terminology kind of thing. And once we have defined things this way, even for non-tensorial component also, you could have a boost weight. The boost weight is defined, if I define it this way, number of how it is scaled under this transformation, boost weight is defined even for non-tensorial object. Like for example, this dA square is 2VR minus so here this x, omega I, and hij, these are not tensors. Okay, not covariant tensors with respect to the full tensor, with respect to the full space-time metric or coordinate transformation. But they, under this boost weight, they have a different property. So they are covariant under boost transformation in some sense. Like x, yeah. See that in the metric, since there is this r square which cancels the scaling of the v square, the x will not scale at all. So it will have boosted 0. Similarly, here this r will cancel this scaling of dv, so therefore this will have boosted 0. This will also have scale. So x, omega I, hij, all can have boosted 0. So del v, this is an operator which has boost weight plus 1, under this scaling it will scale. There will have boost weight minus 1. These are all just scaling of these two things. Now I'll come to the stationarity, maybe then I can stop. The second part to the symmetry is what is stationary. So we are doing, so v going to lambda v and r going to r by lambda will be, and so far there was no stationarity imposed. This could always be done, and this kind of boost weight could be defined be an isometry x for v comma xi. If ax omega I, this is a function of r and v. It's a product of r and v. You see the metric. So if x, omega I, and hij, none of them scales under this lambda transformation, boost transformation. Then if their arguments are also just product of r and v, r doesn't come independent of v, then they're simply invariant. So then the metric will just not change under this transformation. And this particular coordinate transformation generator, in this case, the generator of the infinitesimal transformation this lambda is equal to 1 plus delta lambda is this. This I'll define to be xi mu. The scaling vector. And also I mu at r equal to 0 goes to v del v, which is proportional to the generator of the horizon. So you have a killing horizon. And that means stationarity. So
but r equal to 0 means a singularity, right? R equal to 0 is not the...
No. The way I have chosen the origin of the r coordinate, it's 0 on the horizon.
Okay.
And it's a horizon, so it's r equal to 0 surface is not a smooth spherical surface. It's a surface, not a point, and it's not smooth. So what I'm saying that in this kind of, when we are writing the metric in this fashion, if this metric functions x, omega I and hij, they are functions of product of r and v and xi, then you have a stationary situation. It's a stationary metric. So if Schwarzschild or any other stationary metric we are recurring in this form, all the functions will be functions of r, a product of r and v.
Hello. So just a question. So this form is supposed to be valid even far away from the horizon, or is this a statement everywhere, or?
Actually, if we take a general metric, the way I'm doing it, it seems it's even far away from the horizon. Okay. Because the metric could be written near r equal to 0. This is like, it's not anywhere. It is not, I'm using here that you are near r equal to 0. X could go anywhere. And this is clear that it will be stationary because it's an isometry of the metric system when it's a function of r and v. But I tried to take a car solution into this form, in this structure, and I couldn't do it exactly everywhere in R. I have to do in perturbation. It's such a complicated equation. It becomes so in order by order.
Okay, but order by order it could be done even.
I didn't do it recently, but when I did, I remembered that in principle it could be done to all orders. Unless something happens, like I couldn't did it up to quite a few orders. In Mathematica, it could be done up to few orders.
But maybe these geodesics will, in general, caustic at some point. These are geodesics. Maybe there's a
geodesic.
Not in the Kerr black hole. Not in the Kerr black hole.
Not in the Kerr. Kerr is, it doesn't happen.
No, I'm Shiraz's comment that caustics. Not in the Kerr.
Will not general happen when you take these geodesics that go away from the horizon. These are geodesics.
No, I don't think caustics don't happen. I
see.
Sayantani, so V equal to 0 is the bifurcation surface.
On stationary solutions.
And will you be interested in taking V to be from 0 to infinity or from minus infinity to infinity?
I'll not be integrating on V. I'll do a local calculation at a point. So I'll not, just for the rewriting, V is V at some arbitrary.
Okay. And one comment about this form of the metric and the Kerr solution that you mentioned. So this form is very similar to the Bondi metric, except for this R square factors that you have. So, we know how to write the Kerr solution into Bondi form. So I'm sure by adopting that technology, one can write the the Kerr solution in this form.
Right.
Yeah, it should be possible.
Yes. Actually, the Kerr solution I did long ago, and I'm saying all this, but I can find the Mathematica file now after the talk and Neela told me. But I remembered that when I did it that time, I could do it to all order. It was some nested kind of equation. You first solve for V, then for R, then for V, something like that, like away from the horizon. This is killing horizontality, but continue or let me just quickly do it. On a stationary solution, if I evaluate this quantity, del R to the power nr, del V to the power nd, on a function of x, omega I and hij at r equal to 0, this will be equal to 0 if nv is greater than nr. Is this point clear? Because every day, this is stationary solution. So these are all functions of RV. When you are taking product or any kind of thing, any kind of functional dependence on them. But every del V will take out a factor of R. Then del R can kill them. But if the number of del R is less than in number of del V, then some factors of R will remain. And then if you set equal to 0, this will vanish. Is this okay?
Yes. Yeah.
So
Shantani, would this be a natural stopping point, or
I could boost it weight and differ. This will be just a few, 1 or 2 comments. I want to relate it to stationarity. That's it, and then we can stop. Yeah. So on the horizon, this implies if NV is greater than NR, this implies away from stationarity. And on the horizon, if some physical quantity, anything, is product of 2 such terms where NV is greater than NR, each of them. So what I'm saying is this del R, del V, NV, X, omega I, hij. And then there is some another term, which is del R, MR. So here it is dynamical because it's 0 on the stationary solution. So if NV is greater than NR and this is that means dynamic situation. Similarly, here also it is dynamics, because MV is greater than MR. And if something is product of 2 such terms, it is nonlinear in dynamics and will be ignored in our analysis. Amplitude. And okay, here I could stop just one line that this number of del V. Shall I? Okay. Just one more thing, I'll relate it with boost weight and then the review of all will come and there I'll stop.
Sure.
Okay. Boost weight and departure from stationarity. in tensor component products of x omega ij and their arbitrary del v, del r, or del I derivatives appropriately contracted. These are the only things allowed on, like only things possible on the horizon. This x omega I, hij, and their derivatives. On horizon, as we have previously seen, del v and del r are only operators or on objects, not on with non-zero boost weight. For any tensor with W must have number of derivatives minus number of del R derivatives equal to W. Because these are the only thing that can give you some boost to it. Del V will give you +1, del R will give you -1. So if any tensor component, if we evaluate on the horizon and it has boost to it W, then that particular object on the horizon, this must be the true. This must be the case. Now, W greater than 0. The component must vanish. Oh, my daughter has started shouting. Must vanish on stationary solution, because I have seen that if number of del V derivatives is more than the number of del derivatives, vanishes on the horizon. লিংকে আমি এটা করে নিয়ে আসছি। Positive boost to it, it is nonlinear. It's nonlinear. So all non-zero terms, all terms that seem to be related to the number of V derivatives and del R derivatives on the horizon, anything that has non-zero boost rate, that term is dynamic, is non-zero only in a dynamical situation, and there are product of two terms which with two positive boost rates, it must be nonlinear. So that's the relation. So you calculate in the, you'll have an identity with involving mu and its components, and then we'll analyze the boost weight of all the terms, and terms which are product of positive boost weights we'll say nonlinear and ignore, and the products which the terms which are positive boost weight but not products are the terms that are involved, and we'll analyze. So that will be the key of the proof, like P steps that we'll be using. It's very fast here. Is it clear so far? Or any question here? I can stop here then.
Sayantani, just to understand this second last statement. So you are saying if W is positive, the component must vanish on the horizon of the stationary metric. Is that?
On the horizon of the stationary metric, yes.
Yeah. Okay. And if I understood correctly, you said that if I multiply two tensors, two components of a tensor with boost weight W1 and W2, then you will get a tensor, a component with the weight W1 plus W2. That's the.
No, I'm not saying that. If you are multiplying two components of boost weight W1 and W2 and both are positive, then both are non-zero only in dynamic when there are dynamics. So it's a quadratic term in dynamics.
So
and therefore it will be ignored.
Yeah, you will ignore, but suppose you don't ignore and you insist on asking what is the boost weight of that, then will it be W1 plus W2?
It will be W1 plus W2, yes. Boost weight, it's a scaling, no, lambda to the W.
The scaling, so it will add.
It will add that. But you can have another linear term with boost weight W1 plus W2. That will not be ignored, but this one will be ignored because it's a product of this.
Also, you have to keep track of the.
I have to keep track of this thing, which are the products and which are not. Okay, next I'll do this. Arunwal has used this thing to get some result and we got a current. So if you have time, then I can out at what point this proof was not exactly going through, and from there onwards we explored that point and found the current unexpectedly. We thought that something else will come up, but current has come up. Okay, I can stop here.
Yeah, so let's unmute ourselves and thank the speaker.
Thank you.
So, are there any other questions?
Sayantani, suppose you had a solution which was dynamical, slowly dynamical, in the sense that locally everything is slow, but it builds up to something big. So in the end, the black hole has gone to twice its size, but things have been thrown in relatively slowly. Presumably, your proof will continue to work there as well.
I think my proof will work there as well.
So it's not. It's all. Everything is local. So the fact that there's
local,
horizon locally is enough for you, right?
Locally is enough. We don't need to know.
Right.
Yes,
so where it's not working is if there's variation and it's rapid.
If the variation is rapid, yes. Like when the terms that we are ignoring as nonlinear terms are not ignorable, they are also contributing.
Yeah, and if I want to understand what slowly means, would that be sort of compared to the temperature scale of the horizon? I know in your proof you're very precise, but I was just trying to understand if we went.
It's a temperature scale of the horizon. Amazing. It is the.
Suggest like. Problem. Yeah. Okay. Yeah. Question. Yeah. I don't know.
I can see that del V it's not that loop part. Okay, I can see temperature scale coming in because temperature is the property of the stationarity. Is that making it slow? It is slow in a sense of some. It's not slow actually.
Sorry, you're breaking up. Sorry, I can't hear you.
Sorry, and where is entropy?
Hi, Shantini, can you hear us?
Where is entropy of this object?
She's not yet got to the entropy part. She's going to do some analysis and prove this JV and JI, and that will be the entropy. That I think will come in the next talk. You know, Sayantani is in Mount Abu on a holiday, so maybe she's had internet trouble.
Yeah. So maybe we can stop here. And then for the second part, we will just discuss when we should fix it, and then we'll send out an announcement.